Hello, and thank you for joining us for a STELLA webinar with our special guest, Dr. Craig Kohn. So, I'll go ahead and introduce myself real quick, and then introduce our wonderful guest here, Craig Kohn. So, my name is Mike Taylor. I'm with the Landsat Communications Public Engagement Group, and I'm also the STELLA team lead. All right, and this is our amazing, wonderful, awesome guest, Craig Kohn, and I've known him for over a year now. I met you at Commodity Classic in 2024, and all the educators there were like, "You got to meet this guy," and I did, and it's just been amazing ever since. So, with that, please go ahead, Craig, introduce yourself and go forward.
All right, appreciate it. That's high praise. Howdy, folks. So I am just getting off of teaching here. I've been at a full day of teaching, so I'm like playing catch up here. So if I seem a little like flustered, that's why I just got done with the class and rushed over here from a different classroom. So the joys of teaching. So I'm going to go ahead, share my screen here in just a second. We want that one, and it should look like that. Hopefully everyone can see it. I have a couple students coming in here. One of them just joined us. So in a moment, you might see some faces joining me. These are students we have here at Waterford High School who have worked on the STELLA project with us. Yep. So if you want to come around, you can say hi. So, for example, the phenomenal Luke Osgood is here. He'll be talking with us briefly about his experiences as well. So, actually, yeah. So you should be able to see my screen. Mike, does that look right to you?
It's looking pretty good to me.
All right, perfect. So let's dive right in. So, quick overview of what we're doing here. This is actually a presentation that I did at a Wisconsin Society for Science Teachers conference. That's kind of our state NSTA version. And this was way back in March we did this. We were going to record it. Unfortunately, what happened was we lost Wi-Fi. Luckily, I already had the presentation open, so I could go through it without being in presenter mode. But we're doing this again in part so we can reach more people, in part so we can have a recorded version, and in part because it's such a great story, we love to tell it as often as we can. So I'll briefly talk about who I am and why I'm here. We'll give an overview of STELLA and what it involves and what it looks like and how it can be used. I will do a demo of how to assemble a STELLA Q2 model and how to program it. I'll show you some sample curriculum that we have, and we'll have some time for Q&A here at the end and have some students chime in about their experiences and all that sort of stuff as well. Throughout this entire presentation, if you're interested in getting access to the links or anything we use for resources or curriculum, all of that is publicly available. All of it is open source. You are welcome to use it as much as you want, modify it, change it, however you like. That's why it is there. So if you happen to have a device with you, these QR codes will take you to my website where everything is located. The purple QR code will take you to this presentation where all the links are found. If you happen to need it, I'm going to go back a slide here real quick. And you can see that our bit.ly link is up here. So bit.ly/WSST-NASA will take you to this presentation as well. So we're trying to give you as many ways to get to it. I will have these links and things at the end as well. Without further ado, why would you want to do this? Well, you can learn about the spectrometers themselves, how they work, how they might help you, how they might work in your classroom. We'll walk you through how to build one. They're very simple to build, not quite as simple to program, but it's still very feasible. I can do it. I'm not a programmer. We'll talk about real world applications, especially in ecology and agriculture. So if we invited science teachers and agriculture teachers, so I'll be talking to two different audiences. This very closely aligns to everything that you do. I know because I do both of those things. Currently in the classroom, I teach both ag classes. I have 2 of those, and I have 3 science classes. So I have my feet in both worlds. We'll talk about how this can be integrated in terms of what your students could do for projects, and we'll have some of those folks coming in here and broaden your understanding of what these standards are and how they work. My doctoral advisor was one of the people who was the impetus for NGSS. And so he was the head of our research association when it was created. And I was one of the authors of the National AFNR academic standards for agricultural education. So I know a lot about these. We try to incorporate that into this as much as we can so that people have a stronger understanding of what they're actually trying to do. But no one cares about that. Let's dive into the more important things. This is also something you may not care about, but I got to say it anyway. So, hello, I'm Craig Kohn. I am a teacher here at Waterford Union High School. I've been teaching for 18 years. You can see my background. There's a lot of stuff I'm affiliated with, but the big thing we're talking about here today is STELLA. So, I also have research experience with the U.S. Department of Energy at the Great Lakes Bioenergy Research Center. I was a research fellow with the National Science Foundation. I currently live on a farm here in Wisconsin, and I teach in a small, tiny rural school called Waterford High School. We have another one of our students with us. Do you want to wave hi? Yep. They're going to be coming and going because we're a school. That's how it works. So this is Cheyenne. She's one of our researcher extraordinaires. But yeah, let's just dive in. So what is STELLA? STELLA is an acronym, stands for Science and Technology Education for Land and Life Assessment. The idea of the project is that we're providing low-cost DIY spectrometers that you can build in a school for a pretty affordable price. So it's not cheap, but it's pretty affordable. The idea is that we're giving students access to opportunities for remote sensing data opportunity, like data collection, right? So how can we use this kind of data to address real world questions like how should we produce food, or are our habitats under attack by a disturbance or something like that? Cheyenne, it's weird that you're back there. It's like you're in the, you're like the ring girl. Really quickly, what is spectral data? I mean, we're assuming this is primarily an audience of teachers, but the idea is that we're looking at electromagnetic radiation. So we know that light and infrared radiation are just different size wavelengths of the same moving energy or same radiation, right? So we know that light energy is smaller wavelengths, infrared energy, the energy we feel as heat, is larger wavelengths, but it's all electromagnetic radiation, as is X-rays, as is gamma rays, as is all of these stuff. And so the STELLA units are able to detect 18 bands of that electromagnetic radiation at those different wavelengths. So the idea is, again, we're offering an affordable opportunity to collect this kind of data in schools. And this is mimicking what is found on the Landsat satellites. Obviously not the same quality, but it does the same kinds of things as the Landsat satellites do. They detect infrared and light radiation at different wavelengths to address different kinds of questions. The one that we really focus on is something called NDVI, which we'll talk about here in a moment, but there's a lot of other things we can look at as well with this data. These Landsat satellites, and there are now 9, I believe, if that's correct, right, Mike?
That's correct. Landsat next due to launch 2031.
Yep, so soon to be a 10th. And we can see that they're looking at the Earth's surface, and the current satellites are looking at a pixel size of about 30 by 30 meters. That's about literally the size of my class. Well, no, just under the size of my classroom right now, right? So just over. Anyway, doesn't matter. The Landsat next will be looking at a much finer precision. That's going to be great. There's also one called PACE. That's primarily looking at ocean ecosystems, but same kinds of things. What are we seeing for reflected heat and light? You might be wondering, well, why do we care? Well, that tells us a lot of information. And primarily the one that we're looking at and we'll be talking about in this presentation is known as NDVI, or Normalized Difference in Vegetation Index. In a nutshell, that's the ratio of reflected heat and light, absorbed and reflected. And so if we compare the amount of light to heat that is reflected, we can get a sense for how well plants are functioning and performing. So for example, during photosynthesis, we know that light is absorbed and transformed into chemical energy. That means there's less light that can be reflected back into space. And so if we see less light reflected and more heat reflected, we know we have a healthier plant and we'll have a higher NDVI score. So we can see that in the image here on the left, 0.72 is closer to a maximum of 1.0. On the other hand, if we have an unhealthy plant, it's not going to absorb as much light during photosynthesis. More of that light will be reflected back into space. That will give us a lower NDVI ratio, and we'll be closer to 0 or even as low as -1. We'll talk about that more in a moment, but that's the gist of it. The less light that's reflected, generally the more healthy the plant, because the more photosynthesis that's occurring. And so we can see that in this example. So for my last presentation, when we did this in front of actual people in March, I had 2 plants I snagged from Walmart. And lo and behold, there happened to be unhealthy plants at Walmart, which worked out really well. So I bought 2 identical ones, one that was healthy, one that wasn't healthy, as well as one of their fake plants. And I took these devices and I measured NDVI using them. And we can see that the healthy plant had a higher value. We're closer to the maximum of 1.0. The less healthy plant had a lower NDVI, and then the fake plant was way down below 0.5 because it's obviously not photosynthesizing if it's fake. And so this gives us a sense for how well plants are performing by measuring the amount of light that is reflected back in comparison to the amount of infrared radiation. We can do really cool things with this with the Landsat satellites and the data they provide. One of them is the Earth System Data Explorer. So it might be that you're not able to make these instruments, but you can still use that same data. And so, for example, if we look at the ones I already pulled up, there it is. Let's make this nice and big. Mike, can you see my screen okay?
Yeah, you're good.
Awesome. All right. So, for example, what I plugged into this system was looking at the biosphere and vegetation and NDVI in May of last year, 2024. And then on this side, I did July of last year. And so we can see as I scroll from May to July, our coloration gets greener. And based on the scale, that tells us a better or higher NDVI level, closer to 1. That means
Are you
that
sliding it right now? Because
I just slid it. So this
okay,
would be May.
because I'm not seeing it if you are.
Oh, okay. Then, well, you just have to take my word for
Yeah,
it.
and someone's asking if you could make the screen bigger as well. But
Absolutely. So, so it's only showing that one tab. And I don't know why, but doesn't matter. If you could see what I just saw, you would see the slider moving back and forth. And you can see on the left is May with lower NDVI levels, and on the right is July with higher NDVI levels. And so you can zoom in anywhere on the planet. You can set your parameters for different things or different times or both. And you can see how NDVI changes as we go from season to season or year to year or place to place or anything like that. One thing you might also notice in this image is that we have Lake Michigan and Superior, and they actually have negative NDVI values. And that makes sense, right? Because the light hits the surface of the water and reflects back, and the heat is being absorbed. So it's just the opposite, right? So plants absorb light and reflect heat. Water reflects light and absorbs heat. And so we're going to have negative NDVI values where that cold water is in the Great Lakes. So cool stuff. All right. And for some reason, when I did that, that screwed up my, let's try that again. Mike, is that any better?
yeah, I mean, it could be worse. Wi-Fi could be out, so.
You know what? We're just going to roll with the punches here. So, okay. A couple quick things to show. Again, I'm not going to go into too much detail. If you want to go back into the presentation, all this stuff is linked and you can get this anytime. But some examples of things we use in this way in our classes include this slide. So in our agri-science class, we talk about changes in greenness over time. And so, for example, we can see changes to NDVI from the 1980s to 2013. And we can see, like for us here in Wisconsin, in the Midwest, we are in the red, which means that NDVI values went down. We have less photosynthesis now than we did 20, 30, 40 years ago. And we can see other areas like California, the West Coast, the South have more green. That means that NDVI values went up, more photosynthesis, less light being reflected. And we can start developing some hypotheses, but well, why would this be occurring? In my class, we then look at water usage next, and we tend to see there's a correlation between where aquifers are being depleted and where NDVI went up, and vice versa, where aquifers are not being depleted, NDVI tends to go down. And we start to form some hypotheses and questions about, okay, are these two things connected? And we can start to infer that, well, maybe excess irrigation is enabling more photosynthesis, but at the expense of sustainable use of water, right? So those are things we can start to investigate, get more in depth with, and actually have a real world connection for our classes. Another example here, this is students who use the STELLA devices to measure their own research. So then this particular case, what the students did was they added caffeine to their treated radishes. We use radishes as a model organism. They're fast growing, cheap, etc. So great for that. And they compared them to the untreated radishes without caffeine. And we can see that the difference in NDVI also correlated to the differences in mass and height. That caffeine literally stunted the growth of our radishes. So they were smaller, shorter, and photosynthesized less, which is kind of cool. And then we can talk more about this. We can assign quantitative assessments where we're looking at differences in percentages, et cetera. And we have a whole format for doing this, which we'll get into. But again, as an example of what students could do with this kind of data. So what do we have for options here? Well, we actually have 4, probably more than that now, right? At least 4 options for STELLA. Mike, are there more?
Yeah, in fact, actually the Stella 2.0 and the Q are basically retired at this point, but we do have a heliophysics one. I would be remiss if I didn't point that out. And the 1.2, which is up and coming, which I sort of teased a little earlier.
There we
which
go.
Is nice and modular.
So this is already out of date, but that's okay because science is always changing. So one we're going to focus on is the Q2. I have tried to do the 1.1s before. So when Mike and I met for the first time in Houston, I was super excited about the 1.1. For my abilities as a non-electrical engineer, it's a little bit beyond our grasp. So we tried to do it. We weren't very successful, middling results. But the Q2 is very feasible and affordable, and that's the one we're going to focus on. So again, there are other options. We'll talk about them in a moment. But for the sake of making things feasible and easy, we'll talk about the Q2 primarily here. So the Q2, which is the more feasible one, detects electromagnetic radiation in 18 non-continuous bands ranging from 410 nanometers to 940. So we know visible light is somewhere between 410 and 7-something, 60. More of a biologist than a physicist, but you get the idea. So we're going a little bit beyond the visible into the infrared, the energy we feel is heat. One important note is that it's 18 non-continuous bands. So any astrophysicists out there who want to measure like spectra from stars, unfortunately, we're not really fully capable of doing that with this particular unit because it's not continuous detection. We would need continuous detection of light and infrared radiation to make those inferences, for example, about what kind of elements are found in different stars or in the atmospheres of different planets. So we can't do that. But we can do things like NDVI, which is really cool. And so this is a great introductory option. It doesn't require the soldering or engineering skills or anything like that. It's really just a plug and play kind of device, very feasible to program. We'll get into the examples of how that works here in a moment. As far as the budget, the last time we did this, it cost us just over $150 per unit to get this to work. These are things that are generally available. Most of them are coming from two companies, Adafruit and SparkFun. They can have things to you pretty quickly. Our folks here at NASA sent something to me, and I had it in about 4 days. It arrived yesterday, and you're going to see some of those components here. So generally can be pretty feasibly done and affordably done, unless they're short on parts, which does sometimes happen. So if you're planning on doing this, I would say order stuff early. So if you think you're going to do this in September, order stuff this summer. That way you give them plenty of time. Last year, or at the start of this year, when we tried to order some things in September, we didn't get some parts till November. So it can be hit and miss. But again, the gist of this is that it's usually affordable and feasible. How we assemble this? Well, we can get into it in a moment. I'm going to switch my camera over and stop sharing, and we're actually going to assemble one together here really quick, just so that we can see what it looks like. So let's switch that around here to this camera. And we're hoping that camera's going to, there it comes. All right, so
awesome. There you go.
Let's turn on a light and we can see. So on the STELLA website, you can print off all the components and it looks like this. And so I have all these scattered around, but basically all you have to do is line up the components on the summary and the description and the picture of each item. So for example, we have a microprocessor called the Thing Plus. It's a weird name, but that's what it's called. Thing Plus 2040 microcontroller. So I'm just going to put that there. And I've already connected that to the green button right there. And then over here, I have the power button and battery. So all I'm going to do is line up each component of that. If you hear chips crinkling in the background, that's because I have kids here eating after school.
Can I mention that this layout and all the Stellas were developed and created by Paul Morell, who's a genius, and he's here in the panel as well. So if you have any, technical questions, or if you're like, wow, that's amazing, that's a lot of that is Paul. Pretty much all of it.
Yeah, and yeah, I don't want to give any confusing ideas that I had anything to do with this. I'm the one just figuring out how to use their brilliant ideas. So just to be absolutely clear, but that's the genius of the system is, again, all you have to do is line up each part. So for example, there's only one way these can plug in. So you just look at where the pins are in that port, and then you line up the holes in the cable. These are quick cables, so they just pop in really easily. And now we've just connected the clock. And then I already have the battery in the clock. Then we'll take another wire and we will connect the triad sensor. This is what actually detects the infrared and light radiation. And we just plug that in like so. If it doesn't go in easily, don't push hard because you can easily bend the pins that are necessary for that connection. And then last but not least, we're going to connect the display. And voila, we have a unit. Now, there's a couple of things you could do. Obviously, this won't be very functional when it's just a bunch of loose wires all hanging out. So one option is you can 3D print their housing. So this is what it looks like when it's all nice and fancy. Or this is what ours look like. This is what we printed in the library. Or what you could do is then just take a jewelry box and just throw everything in there. Just make sure you tape it down nicely, because if the wires jiggle, it can throw off your programming. But it doesn't have to be a fancy housing. It can just be, this is probably $1 on Amazon, but it works just fine. In fact, yesterday I tested these two side by side, and I got almost the exact same data and the same readings for each one. So it doesn't have to be the fancy housing. If you have a 3D printer, that's great. just be aware you have to be pretty precise. One mistake we made was they didn't have like the 100mm cables, so we went with the 200, and that was just too much to try to cram into this little space. So if you want something that's a little more forgiving, then just go with the jewelry boxes on Amazon, which is cardboard. It's nice and cheap, and that can keep your cost down a little bit easier. Or if you don't have a 3D printer, that's another option. But that's all there is to it. You just got to plug everything together, and you should be good to go. We still have to program it, obviously, but that's the gist of it. That's how we put it all together. So with that being said, if we have a functional STELLA unit, the next thing we'd have to do is program it. And so we'll briefly go over the programming instructions, and then I'll do an example with you. I'm going to go ahead and reshare my screen here in just a moment. So hang tight, screen, and I'm going to do this. So I'm going to share my window instead. That way you can see it a little bit better. Mike, is that coming across okay?
Yep, looks great.
Okay, awesome. All right, so let's start at the top here, programming instructions. Now, they have all of their programming instructions on their website. We just rewrote them to make them a little bit more feasible and updated based on the new options. So they're just released. You just had on Friday a new version of the coding released, right?
Yep.
Yep, so they're updating things all the time. So these are almost like living, breathing devices in the sense that there will always be updates. As a biologist, I like to call that evolution. But nonetheless, first things you have to do if you want to program one of these things is download 3 things. The first thing you have to download is the programming file from CircuitPython. It's a weird looking name, but that's just what it's called. So this is the company itself selling. It's called SparkFun is the company. They're the ones who sell the Think Plus, which is like the brains of this device. And so you have to download the program file by going to this website and then clicking that purple button that says download UF2 now. UF2 is the programming file. You also have to download something called the Mu editor. I like to call it the Mu editor because I'm from Wisconsin. But the Mu editor is how you do the programming for the clock. So again, all these are free. They're easy to get. You just go to this website, hit download, follow the instructions, you're good to go. The last thing you have to download are these STELLA files. So STELLA is the instrument, Q2 is the instrument. Go to that website, download STELLA Q2 files. It'll download as a zipped folder. So you right click, hit extract or whatever your computer system uses, and then you will have all the files you'll need to program your STELLA. And that's it. Once you have those 3 things, then you find your stuff. First step is to plug in your device. So you're going to use a USB-C drive or a port. You're going to plug that into your laptop or computer. You should see it come up as RP1, RP2. You find the CircuitPython file in your downloads, click and drag, and what will happen, and you'll see this here in a moment, is that file will essentially rename itself as CircuitPython. And so it'll look different. Your computer might say you should have ejected it. It'll yell at you. That's fine. Once you have that, then what you're going to do is go to your downloaded STELLA files. You're going to find something called the Q2 all folder, and you're going to find a lib and a code py. You're going to highlight both, click and drag, and now you've added the programming instructions to your STELLA Q2. Once you do that, you have to set a clock. So that way your device knows when it is, because you're going to need that to figure out what data was collected when. So if you know when it was collected, you can find it more easily. It's obvious stuff, right? So to do that, you're going to go in your STELLA files. There's going to be a folder called clock set. It's also going to be called code py. You're going to click and drag that onto there. And then you're going to go into a program called the Mu editor that you downloaded earlier. And it's going to say, what year is it? And you're going to type in the year. And it's going to ask, what month is it? And you're going to type in the month. And you just keep doing that till you have the universal time set on your device. And we'll show you what that looks like here in a moment. Lastly, when you set the clock, you actually override the original files you used to program it. So you have to add those back. So then you're going to click and drag the original code py file you did before. That will replace the time file. And then you're pretty much good to go. So we can do an example of what that looks like here really quick. Give me a moment because I have to take an original unit. So the one I assembled for you was one that I programmed earlier. So I'm going to plug that back into here, and then I will show you what that looks like here in just a moment. I just erased everything on it, so it should be a fresh start. Now, of course, because we're doing this live, I'm sure something will go wrong, but hopefully not. So let me unshare. Actually, let's pull up this file. There we go. Mike, can you see my files okay?
No, right now I'm still seeing just programming instructions.
All right, so let's try stop sharing, and let's pull up this. It was supposed to share my, let's see, I should share my screen window. Let's do entire screen. That probably will do it. And let's try this one. All right, now you should see my files. Does that look right?
Yeah, that looks right.
Awesome. All right, so I just plugged in my STELLA device, and if I did it right, it should say, it doesn't say that, of course. Well, okay, that's fine. We'll make it work. So right now it says Circuit Pi. Originally it should say RP1, RP2. So there's a quick fix I can do. If I ever have a problem, there are buttons on the back of that Thing Plus that say boot and reset. And so if I press boot and then press reset, what it should do is completely wipe it clean. And if I go back to my files, hey, look at that. It worked. All right. I've done this a few times in the past week. So it says RP1, RP2. That means it's a fresh drive. There's no programming on it. So the first thing I have to do is add the Spark Fun actual programming files, the U2 or UF2 file. So I'm going to go into my downloads, and I'm going to find that UF2 file. I'm going to click and drag that onto there. And if it works, we see it's loading up.
And just to note, the UF2 file usually does come in the whole package, the Q2 all.
Okay, so that sounds a good sign. And now it's renamed Circuit Pi. Hey, good to go. All right, so next we have to add the programming files. So I'm going to go into my downloaded STELLA Q2. I'm going to go to Codes and Libraries, and I'm going to click both. So I have to hold Control on my keyboard, click both of these files, the folder and the file, and I'm going to click and drag. And it's going to ask me if I want to replace. I do. And we wait patiently on my very slow school computer. And in a moment, I will have all of the program files I need on my Q2, and it should be fairly operational at that point. And so, for example, if I bring over the Mu editor and I click on Serial, now it's communicating with the device. So the coding program and the device are talking to each other, and it's saying, okay, at these 18 bands at which we can detect things, we are getting some data. Awesome. So we have a functional unit. The only thing is it doesn't know what year it is. So it might think it's 2000 and in Sinkston style, it might think it's 2045 and the world has ended. Who knows? We have to add the clock information. So to do that, I go back into my STELLA files. I go into my test codes, and the top folder will say clock set. It's also called Code Pi, so I'm going to click and drag that onto there. I'm going to replace it. And now it's going to ask me what year it is. Mike, in a moment, can you get the universal time ready?
Yeah.
I don't have that open just yet. So I know the year is 2025. I know the month is 5 for May. The date is 20. Now we need universal time indicator. So we don't want our local time. We want the universal time. Mike, do you know what the hour is?
Yeah, it is 20.
And what's our minute?
29.
29. And what are our seconds?
About 10 seconds. I usually put a
Cool.
lead time in there.
Yep. Okay. And now we can see it has the right year. So if I kept hitting enter, cycle through the month, the year, the date, all that. But right now it looks like it's right. So good to go. We set the clock. Last thing we have to do then is go back and add our programming files, because when we set the clock, it overrides that. And it's just a thing you have to do. So we go to Code Libraries. The only thing I need is that Code Pi file. That's the original one I put on there to add the programming instructions. I'm going to click and drag. I'm going to hit replace. And once that uploads, I should have a functional unit.
Cool.
If I go back into the Mu editor, I can see it's now communicating. It turned on the lamps. It's talking to the sensors. Life is good. Everything is working. We have a functional unit, and we just programmed one in front of you. So, la-di-da. All right. So,
can I interject real quick?
Absolutely.
I just wanted to say that CircuitPython is an independent nonprofit, not SparkFun. Just note.
All right. With that being said, so we did our programming instructions. We can move on to what can we actually do with this. So let's user instructions. So we can see that there are 2 buttons. So if I take this one here, so first things first, obviously you have to keep yours charged, right? So it's not going to work with a dead battery. The quirky thing about these is they have to be turned on to charge. So you have to hit the on button, which is the black one, then plug it into a charging cable. Otherwise it won't charge. I mentioned a button. There are two buttons. There's the black on off button, and there is the green button. That's for data collection. So the first thing I have to do is turn it on. If it's functioning correctly, what will happen is it will show me the date there. There will be a red and a blue light, and then a white light will briefly flash, and then it should be red. That means it's turning on appropriately. It's going to cycle through some things, tell me the battery percentage. It's going to tell me things like I have an SD card. It's going to tell me how many bands there are. It will mention 3 bursts, which means when I press the green button, it's going to collect 3 points of data for all 18 bands. And then we can take the average of that. That way we get more reliable results. And now if you look closely, it's detecting infrared and light radiation. And so that's what this is showing us right here. Now, this isn't super useful data. We'll get into how to find the useful data. But what this is telling me is that this is detecting radiation as we speak, which is pretty cool. So like if I cover my hand over that sensor, we can see that in a moment here, all of that changes. And when I take my hand away, that's going to change again, which tells us that it's actually detecting light and infrared radiation. Super cool stuff. Okay. Mike, you can see my slideshow okay, right?
Yep, you're looking good, man.
All right. One other thing you're going to note is that where this display is, there is what's called a batch number. So when you collect data, it's not going to be like, oh, you collected spinach leaves or you collected pond water. It's just going to give you a number. So when you download your data, you're going to have to know the time or date and that number in order to figure out what's what. Otherwise, you're just going to have a bunch of numbers on a screen, which you'll see here in a moment. So that is a downside of this, is we can't get the data just from looking at the instrument. We actually have to take out the disk and plug that into a computer to get the data. C'est la vie. That's what you get for the more lower cost entry models. But we'll get into other options in a moment here as well. All right. One last thing, calibration is key. So in between collecting data, you always want to have some kind of like white paper or foam, and you want to hold your STELLA unit. So just generally speaking, the size of the data collection area is roughly equivalent to the distance it is from that object. So for example, if I want to collect an area the size of this disk, I need to be the diameter of that disk away. And so whenever I'm collecting data, I want to calibrate to make sure that my data is accurate and not being thrown off by something, right? So I'm going to calibrate, collect that data. Then I'm going to measure my data, boom. Then I'm going to calibrate again. Simple as that. And then you just keep doing it, calibrate, collect data until you have all the data you want to collect. All right, so what does that data look like? Oh, and one last thing, there are 2 ways you can collect data. So there's the single mode, and there's continuous mode. So like if I want to connect this to a drone and fly it over a field or a forest, I obviously can't push the button if it's 50 feet in the air. So then I have to switch to continuous data collection mode. To do that, I just hold the green button. Simple as that. If I want to go back, just hold it again. Mike, about how long do you have to hold that button?
To collect data?
Yep.
I mean, it's just a brief tap. Did you mention the holding it on for 3 seconds?
Oh, that's what I was getting at. So if I want to switch between modes, it's 3 seconds.
Oh no, between modes it's just a tap. Yeah. So, but if you want to, you can turn on the lamps if you hold it down for about 3 seconds.
Okay.
So.
I don't really use continuous mode because we don't have these attached to drones yet. Our goal is to eventually do that. We have a research field. We'd love to fly it over and collect data. Still working on that part. So, and it's also early in the year. So there's not much to collect data for yet because nothing is growing yet. Anyway, if you want to retrieve your data, so inside the STELLA, or in my case, it is on here on the side, either works. There will be a mini flash, or not flash drive, mini SD disk. So if I pull that out, it looks like this, and I'm just going to plug that into my computer. And when I do so, it's going to give me data that looks like this on the side. So you're going to see it has our universal ID. That's the number that's specific to your unit. It's going to give me the batch number, and it's going to give me a lot of other things. Big thing that I'm interested in is the intensity of the radiation at different wavelengths. So this is, if you look at my screen, 410 nanometers, 435, 460. These are the 18 bands of radiation at which it collects data. And next to that is the intensity of that data measured in microwatts per centimeter squared. Microwatts is right?
Yes.
There we go. All right. For NDVI, which measures how much photosynthesis is occurring, I really only need 2 points of data. So it gives me all 18 bands, but I just need 8, 10, and 645, because that's how we calculate NDVI. We take the intensity of the radiation at 810, minus that at 650. We don't have a 650, so we use 645. So 810 minus that at 645 divided by 810 plus 645, and that will give us some kind of fraction or number, which in this case was pretty low. We can see up here data we collected for, I believe this was our agri-science experiments in fall. So we had different treatments, be it caffeine or fertilizers or anything like that, and then looked at how did that affect NDVI. And again, to do that, I just plug those numbers into this formula. I can enter that formula in Excel or Google Sheets, and that will spit me out a number that's between -1 and +1.
Can you zoom in on that a little bit? The NDVI treatment by treatment?
I don't know
Is
if I
there a way to
can.
do that? Okay.
Because
Not,
it's
that's all right.
again, if you can't see it too well, you can get the presentation. I'll have the links at the end again.
Fantastic.
And just, yeah, check it out then. I can share other files too as we get closer to that. Again, here was the presentation data that I did back in March for WSST. And so again, we just used the same unit and collected. So this is the one that collected this data, and then just measured both the healthy plant, the dying plant, and the fake plant. And this was the data I got. Now you can see I collected that data twice. There's going to be some fluctuation. I was doing this in a hotel room. It was like a 40-degree day with like 20-degree wind chill. I wasn't going to go outside, right? So it was also a cloudy day. So as I was collecting this data, sometimes a cloud would move in front of the sun. So one thing that's really good to do is to keep a record of what the conditions were like. Ideally, we're doing this at exactly solar noon on a perfectly clear day, and you have a lot of money and everyone loves you, right? This, not in the real world, sometimes we have to collect data under less than ideal conditions. And so this was that, which meant there's going to be some variability. That's okay. That's life. We acknowledge that as we're doing our write-up and so on. And again, for data analysis, it's going to be reporting the data in what's known as CSV, that's comma separated variables. That translates really nicely to a spreadsheet. And so one thing to be aware of, there's going to be other things in there besides the data you're looking for. So for example, there's uncertainty. It's telling us the range of acceptability, I guess, for our values, if you will. That may not be relevant to you. So it might be overwhelming when you first look at it. Really, the only thing you need is the intensity of the radiation for 2 wavelengths, if NDVI is what you're focusing on. If you choose to do other things, well, so be it. All right. Lastly, there is the 1.0 and 2.0 options. Again, these are going to be a lot more challenging. They require 3D printing. They require soldering. I'm not someone who's good at soldering. That's what they look like. They can do a lot more. They will show you your data on the screen. They have the option of using the NASA data viewer, which is super cool. So you can see the actual results in graph formats and table formats as they're happening in real time. Super engaging for students. They really enjoy that. You just have to have a lot more skill and time and patience, more than I have at least, to make these. So the Q2 is very feasible. 1.1 and 2.0 are much more challenging. But if you have that capability, awesome, you can go for that. So
should note that 2 high school juniors did build 40 of those to send out as loaners across the country. And we are working on the Q2 being compatible with the data viewer up and coming.
That would be awesome.
So,
All right, before I dive into our sample curriculum, we have 2 students with us. I don't want to keep them here all night. So do you guys want to talk maybe briefly about your experiences? Of course.
Awesome.
Then I will dive in with our curriculum after that. So why don't you come on over? You want to grab chairs?
Will they be able to answer questions?
Are you okay answering questions?
Sure.
Yeah, let's go for it.
Hello, my name is Luke Osgood. I have been working in this little STELLA program for a little over half this year. I started before 2025, but this year, my senior year, I'm a senior in high school, and I've had Dr. Kohn before in freshman year, and I've recently gotten back to him to do this STELLA project.
Excellent.
As I said before, I'm Cheyenne Lees. I'm a freshman. I have Dr. Kohn as my agri-science teacher. I started, well, I don't know, I just really had an interest in this in the beginning of the year, so I've been with this all year. So,
do you want to talk about what are some of the things, like what do you do in a typical week with this?
STELLA, we usually meet once or twice a week for 30 minutes each time. We essentially have different tasks we do in relation to the STELLA apparatus instrument. Usually the meetings involve us like workshopping, trying to solve issues with the STELLA like apparatuses, because we try to home make them so we can have them for school projects, for like important data collection. And for example, this is a homemade one. We've been workshopping things like this. We've got like 2 of them working. One of them still like malfunctioning a bit since the start of the school year, because these things, they are somewhat complicated, so they do have a lot of, they're a little finicky. So a lot of it is us workshopping, making sure they work properly, fixing any issues, helping Kohn with whatever he needs. And sometimes we also do tests to make sure they're working properly. So essentially it's constructing, doing little like demos to make sure they work properly. That's mainly what we do in STELLA.
Sean, you want to talk about your Acre Science Fair project?
Yeah, so going off of what we were like working on with STELLA, I had like a deep interest within the NDVI and like its correlations to crop production, especially within like different farming mechanisms like monoculture, regenerative agriculture, BMP practices. And so with using Acres, which is essentially a platform by NASA that like does like it shares the results of NDVI from the Landsat satellites over wherever. So currently me and my partner Logan, he's not here, we're taking the NDVI results of all the fields at Michigan State's experiment thing.
Yeah, so effectively comparing NDVI under sustainable agriculture versus conventional agriculture.
Correct.
For different experimental plots.
Mm-hmm.
Fantastic. Are you doing calibration to get to the reflectance from irradiance to radiance and then reflectance? Are you using those steps for comparison?
So yeah, you would calibrate between every.
Yeah, we do calibrate in between.
Yeah, so when we do it, I typically write down like what we're doing. So I have like a line through the middle of paper, splitting one side being like the not the calibration, the 2 things that we're like measuring. So then between each treatment, I write down the calibration and then the whatever we're looking at. So for fall, we did stuff for radishes. So we put radishes there. We put the batch number, time, and conditions like cloudy, sunny, whatever, just to stay accurate. And so they're easy to find when we're looking at the data.
So a lot of the data we saw in the presentation was coming from those lunch experiments where they were coming in, collecting the data, and then preparing the spreadsheets.
It's fantastic. Excellent. Well, and then so if you had any improvements or anything like that for the STELLA, what do you think you would improve on it?
I would say definitely start with large enough cases. A lot of it, we had troubles fitting all these instruments, all these parts into these small cases. A few times they were damaged because we were trying to fit them in and we had to like remake them. It was all big, kind of like a little hassle. So I definitely start by figuring out how to properly create these. I also wish we did have more time to work on these because we don't meet often. I mean, I've been really busy. I haven't been able to do many meetings, but still, I'd like to meet more often for this. I know that's not like your guys' problem. It's because we're all so busy. But yeah, these are very labor intensive to make and test.
Very cool. Well done. That's great. I'm glad that you're getting use out of them and enjoying them.
Mhm.
Do you have any questions, Craig? Or anything that I've missed so far?
Last
Anyone in the chat?
thing I was going to do is go through the sample curriculum. So
Okay.
I don't know if we have any questions from anyone attending that we want to address first. Otherwise, I can dive right into the sample curriculum.
I'm not seeing too much from the chat at the moment.
Okay.
I've seen people saying very, very cool, well done, students. And I have to agree, that's fantastic. So I'm glad that you all are having fun with the STELLAs and enjoying yourselves and learning things. So, and it's all part of the process. Another good job for you all from folks. So,
All
take
right.
care.
Thank you, folks. All right, let's dive in then to some sample curriculum. So I'm going to share my screen again.
Okay.
And screen, we want a window, and we want this guy. All right, so Mike, are you seeing my slideshow?
I am seeing your slideshow.
Awesome. All right, so folks, we're going to briefly go over what an example of a curriculum could look like. This one is for agri-science. We actually just had our main agri-science teacher walk in, Mr. Wicks, so we can hear from him here in a moment as well. So I'm actually not the main agri-science teacher. I was at one time, but this gentleman back here is our main one. And so he is our FFA advisor. He is probably the busiest person in the building. And he and I teach agri-science together. So each of us teach a section of it. And that's where we did most of the implementation of the STELLA units. This will very much translate nicely to biology. We do a similar kind of a radish race experiment with them, where at the end of the first semester, they have to design experiments, a la NGSS and all the scientific and engineering practices. And so this lends itself really well to both things. And we'll get into how all this works anyway. If you're wondering why are we doing all these things, we have kind of a unique context here at Waterford. So when I finished a PhD, so I did a dual PhD in science education and environmental science. My goal was to help as many teachers and students as possible. And I didn't feel like publishing rarely seen papers was the way to do that. So I actually went back to my old high school and asked if they'd be interested in hiring me half as a researcher and half as a teacher. And so I kind of fill two roles here where I do teach multiple classes a day. Right now, because I'm filling in for a teacher who just had a baby, I'm teaching full time, but usually I'm only teaching 2 or 3 classes a day. This guy behind me teaches probably about 17 classes a day. And so his experiences are probably a little more relevant and valid, and we can talk about that in a moment. But the curriculum we're going to see is taught by both of us. And the idea is it's open source. Anyone can get access to it. You can make your own copies of it and change it in any way you want. The goal here is to create things that are not just classroom tested, but also classroom designed and fully reflect the realities of very busy people who don't always have time to do everything from scratch, right? That's the goal here. So again, this is yours to use however you want to use it. Everything we talk about can be found on my website. That is www.drkohn.org. If you go to drkohn.com, that's a very different Dr. Kohn, who is a gynecologist in Florida. I don't recommend it. It is educational. I don't recommend it, though. But anyway, drkohn.org will take you to everything you need. And again, the goal for this is to create things that are not just aligned to research and academic standards, but also feasible for everyday teachers to do in their own classrooms. The lesson we'll be talking about is what we call our crops unit packet 1.3. And so what this does, the entire crops unit has 4 packets, and it guides students through how scientists conduct experiments using systematic inquiry in order to draw conclusions about what things we can do to make crops produce more food. Simple as that. And so we're in the 3rd packet of this unit. So 1.3 is the 3rd packet of the first unit. We'll briefly talk about what the other 2 packets look like. But in this particular packet, they're doing data collection. So they're measuring plant height, plant mass, and NDVI, and using that to see if the treatment they applied to their radishes enabled more growth or productivity compared to the control. Simple as that. We're using a few things for this. We talk about careers. We won't get into the details. If you're interested in finding more information, again, this is linked. So up here on top where it says packet 1.3, that is a hyperlink that will take you to it. But in the interest of time, let's dive in. So in packet 1.1, the first unit and the first packet, we talk about, we used to call this a scientific method. In GSS, we talk more about scientific practices. And why should we trust scientists, and how do they get the information they have, and how do they reach their conclusions? We start talking about that. So we have a couple exercises. We also have them plant radishes. So they get 2 trays. One is their control that is untreated, just standard potting soil and radish seeds. And then one they have to apply a treatment to. Caffeine or adrenaline or extra fertilizer or something like that. And then after a few weeks, we measure the results to see if there was any difference. Packet 1.2, we start to get to the atomic and molecular basis for explaining crop productivity. So we talk about conservation of matter and how during photosynthesis, we're turning CO2 and H2O into glucose and oxygen, and how that glucose is the basis for all plant molecules and is necessary for them to grow. So the more photosynthesis, the more plant growth, the more food we have from a field. In packet 1.3, now we're walking them through how do scientists do what they do. So all the standard things, let's first form our question. So how do we do a research question? What are we wondering? Let's turn that into a hypothesis. How do we make a prediction using an if-then structure? How do we do a rationale in order to justify why we think our hypothesis is going to be right, and so on. So very standardized, very scaffolded. And this way we're walking students through what scientists actually do. In part 2, then we start doing data collection. So first thing we do is just measure how tall they got. Then we start getting into plant mass. Before we actually harvest the plants, we have to do NDVI. So we use the STELLA units, we collect our NDVI data. And then we start talking about, well, which of these is actually the more valid measure of plant growth and productivity? And so we get students into these questions of, well, just because I collect numbers doesn't mean I have something that proves or disproves an idea. I have to talk about, is this a valid measurement? Is this a reliable measurement? Do I have enough data to form actual conclusions that are reliable? And so we talk about all the core ideas and fundamental tenets of what makes a reliable research experiment. In part 3, then, they're going to find or draw their conclusions based on their data. They're going to collaborate to determine if these are valid and reliable measurements, and then we're going to connect these to careers. So in the very first packet, they have to talk about what is a plant-related career they might want to pursue someday, and then get into, well, does this relate to it? Is this something that you still think you want to do? So on and so forth. That way we connect it a little bit more to their lives. This packet has an appendix that we obviously added after the fact, so that way we could incorporate more of the STELLA stuff. And so we're getting into questions about what is NDVI, how does this tell us anything about what plants are doing or how they're performing, and how can we use this to draw conclusions? So we have a brief reading, we do annotated reading strategies with it, we have them form hypotheses specific to STELLA and NDVI, and then we actually use the data and analyze it to form a conclusion. And that's what that looks like there. It's a slide you saw before, but this was the data from my class in fall. And you can see the different treatments. Blue was our control, green was our treated radishes, and gray was our calibration. We can see we had a little bit of variability in our calibration. C'est la vie, that is life. And then we can work that into our explanations. Well, we have limited reliability or validity in our data because we know our calibration was thrown off because we had changing conditions from clouds as we were collecting our data. We had to do it that day because that's the only day we could do it. So that's how it works, right? Like getting students into the reality that sometimes science isn't perfect. Sometimes it's messy. It doesn't usually look like a textbook, but that also prepares them to then better design experiments as they move forward in the class. Finally, in packet 1.4, we start introducing them to science writing. So they're given a structured template. Everything they need to fill in is highlighted yellow. There is a rubric that accompanies that. That rubric is based directly on the scientific and engineering practices and the cross-cutting concepts in NGSS. It literally addresses every single one of them. And this is what they do for every single project. So at the end of every unit, they're going to do some kind of research like this. They're going to prepare a presentation using all the standard conventions in science for reporting their question, hypothesis, rationale, data, and so on. And that's the whole thing. So like I say, that is available on the website. All the curriculum is linked on the menu bar on the upper right. So if you use the QR code, that will take you there, or just go to drkohn.org. That will take you there as well. Again, these are free for everyone to use. The idea is that you can make a copy for yourself, change it in any way you want to make it relevant to your students. And that way you have access to things that might help you out and do more interesting things in your classroom if you're looking for that sort of thing. So that is all I have. Mr. Wicks, do you want to briefly talk about your experiences? Sure. And then we can do some Q&A?
Fantastic.
And I was watching on my computer in my classroom. I was like, I figured I'd probably walk over. So anyways, hi, everybody. My name is Mr. Michael Wicks. I am the other ag teacher here. Like Dr. Kohn said, he was here before I was, but then he left and he came back. And it's kind of this ebb and flow we have with him here, but that's pretty normal. I'm finishing my 7th year teaching here at Waterford. And what I really enjoyed about the STELLA is obviously it was Craig's big thing to kind of build them and put them together and do the initial work with NASA in that planning phase. But from my perspective of him coming to me and showing me all this different stuff, it was unbelievably easy to use it in class. I mean, it was literally a click of a button and it couldn't get much more simple than that. And we had really cool, unique sets of data that like he had over here to just add on to our experiments. So like, obviously I was doing the radish race lab since I started because that was part of his old stuff from before. And traditionally it was just measuring height and it was measuring mass, nothing too special, but getting into plant sciences. Adding NDVI adds that next level factor of, okay, sure, I think about in horticulture, sometimes I get these cool tall plants, but does that mean they're the healthiest ones? And then do they correlate then with other aspects just beyond that growth factor, which I thought was really fun for us to be able to add into there. And I haven't played around with it yet too much, but I think the NDVI has really applications in some sort of horticulture or plant science class beyond just this component. It has applications in like an environmental science, natural resources class. If you're doing like a, have you already done something?
Well, I was going to show them our FFA field.
Oh, our field, yeah.
Yep.
Oh, you did pull it up already. Okay. So yeah, so he already pulled up the NDVI for what is our wonderful 16-acre field that we have for our FFA, which actually, and I think I've talked about this a little bit, our leasing agency wants us to adopt a few more sustainable practices, which we already do no-till and other things like that. But they also want to do things with water retention and organic layers and whatnot. So it'd be really interesting to see, like, as we're adopting a cover crop, we're going to do winter wheat this year, how those practices can actually change our own FFA field, but then how kids are, this is part of their thing. This is their project. They're excited to do it. I have a freshman who's all over it. Not Cheyenne, another freshman actually, but he was, not just talking about, okay, we take NDVI, but then does that correlate with the soil horizons, the organic layer? Does that correlate with all these other factors that he wants to get more involved into? So what I think is great is they're simple to use, but the kids do get excited about it, especially when you say, we're using stuff from NASA, and they're like, oh my gosh, what do you mean? NASA, like the big space, all that stuff. They get excited. And that's really cool to see, especially when sometimes it's a little hard to get kids into what you're doing these days. It's really fun. So I've had a great experience with it. I definitely foresee us continuing to use it next year and growing from it, giving more opportunities. Like you said, the idea of hooking it up to a drone to fly it over, different fields, or doing like a survey of local farms and things like that would just be, I think, a great experience for our kids. So I see a lot of promise with this, and I'm really glad we got to use it. So thank you for your time.
Oh yeah, fantastic. Thank you very much.
Yeah, and to piggyback off of that, I will say, so this is the acres analysis program. So again, if you don't have the STELLA units, you can get this right now if you wanted to, and you can just click and drag over an area, and it will tell you NDVI. We did this as a bell ringer one day, and we never got to the content for that day. Like, kids were so invested in this that we literally had a full hour of discussion about. So then they were like starting to look at their own properties or their neighbors and comparing. And they were like, well, this guy always does corn this way, and he always plows every year, and let's see what that looks like. And it was literally just this, like, I didn't even do anything. It was just an hour of them exploring, talking, discussing their ideas. So I will, piggyback off of that. Absolutely, this gets them engaged. They're interested. Having the NASA logo. Like, kids fight over who gets to carry the briefcase, right? So there's a lot of engagement that comes from this, and it gets them thinking much more deeply on a systems level. So photosynthesis can be pretty straightforward, but if we start asking things like, if you look on the screen here, we can see a big dip in August in NDVI, and then it rises again. Let's make some predictions about that. Well, it turns out that, here it says August 17th, it rebounded. Turns out it rained here on August 15th. So why would that change NDVI? So we're getting kids to think much more systematically, much more in terms of making connections across different kinds of content and at different scales and systems. And so absolutely, there's a whole bunch of options and opportunities to get kids engaged and thinking more deeply through this opportunity.
Fantastic. That's great. Yeah, and I'm going to make sure that the Acres folks know that you're using their stuff, because I know they're going to be very excited about that. We do have a few questions.
Yep.
In the chat. And so let's see. I believe it's and excuse me if I pronounce it incorrectly. Heidi Baxter Loffer asks, if you were to use Wisconsin fast plants as your model organism instead of radishes, learners could include number of days to flowers, number of flowers, and number of seeds in their data collection, carrying over into understanding reproductive success and linking that to sustainability and evolution.
Fast plants are amazing. So I want to put out a plug for that. So Hetty and I actually worked together when I was working at the Great Lakes Bioenergy Research Center. So absolutely, so much more you could do with fast plants. We just happen to use radishes because we have like a bajillion of them. And it's just kind of what we were using for a while. But yeah, I would like to get to the point eventually where we could be more systematic, and Wisconsin fast plants would allow you to go into much more detail and depth with those kinds of questions.
Fantastic. Okay. Next question from Sean Gordon. Did the radish you treated with caffeine contain caffeine in the root/bulb would it wake you up like a cup of coffee?
So what we found was that caffeine actually inhibits root growth in radishes. So our conclusion for that was that the main reason growth was impaired is because they're not developing roots to the same extent that the control radishes were. So don't know that for sure. We'd have to look into that further. Good research always brings up more questions, but that's our premise for the moment.
Maybe we'll make them taste good. I don't know. I'm just kidding. Yeah, and so from Keith, is CO2 measuring a function of STELLA? Well, Keith, we have the STELLA AQ, which measures not only CO2 but particulates, especially in the 2.5 and the 10, and barometric pressure and all that sort of stuff. And the newest one, the 1.2, and I don't have the plug-in with me at the moment, actually also measures methane. And we're also looking at nitrogen dioxide and various other things to measure. So that's why it is like, what do you want to measure? All right. The next one. Can you share the NASA Acres GEE API?
So that's something I can plug in our chat here.
I believe so. You should be able to.
Yeah, let's try that. So there we are. There is the NASA Acres program. It's awesome. Really great example. So I plugged in my farm. So my farm is this green little oasis in the midst of the very conventional conventional orange and yellow. So that's mostly because we have woods and typically forests have higher NDVI. But yeah, it's a really great tool. So you can drag it over your home. You can drag it over test areas. One thing that I had shown in our presentation was KBS. KBS is Kellogg Biological Research Station. That's actually where I was for part of the time when I was doing my PhD in environmental science. So it is the longest ongoing ecological research experiment in agriculture. It's been going on since the 80s. And all they really do is use the same method over and over for these different plots. So the blue is going to be business as usual. That's conventional agriculture, tillage, no cover crops, lack of crop rotation, that sort of thing. And then red and pink are going to be more sustainable methods, things like no-till cover crops, more rotation, things like that. So, and you can see how well it lines up with that, right? So that's actually the Agri-Science Fair project that Cheyenne was talking about, where they're measuring average NDVI for the last growing season for each of these plots to see how that affects photosynthesis. So super cool stuff. I highly recommend.
That is really cool. That's, it actually kind of reminds me of a fuse box from a car from seeing it at this distance. But so another one from man, again, maybe I'm saying it wrong. Heidi? Is it Heidi or Hetty? Hetty. Okay. From Hetty. Are you able to use STELLA to measure anthocyanin concentration in leaf and stem tissue? That's a good indicator of stress. In fact, is part of what scientists in NASA's LEAF project will be looking at as an indicator of stress in fast plants grown on the moon. Would STELLA be able to quantify that pigment concentration as another variable to compare? I don't know.
I don't know. Yeah.
Okay. I was letting the agri-science person go.
I don't think, I mean, it wouldn't be that specific. You would probably see differences in, I guess it would depend on what wavelengths of light that would pertain to. So I guess possibly it could. If you knew that anthocyanin had an effect on a particular band of wavelengths, you could see if there was a difference in stress plants versus not stress plants using those wavelengths. I don't know how that would work though, specifically. But potentially. I mean, that's the thing, is like you could compare data and see, well, is there a significant difference between plants in this group versus that group at these different wavelengths, and then start making inferences from that.
Sounds like Hetty needs a needs a STELLA to play with. So excellent. And that's the end of the questions at the moment. Does anyone else have any more questions? Give you a few seconds to type it out. If not, I mean, that was a fantastic presentation. And again, you're always great, and it's always great to chat with you. And it was fantastic to see the students. And it's Dr. Wicks, right? In the background?
Yeah, Mr. Wicks.
Not Dr.
I don't have a doctor.
No, Mr. Wicks. Sorry. Yeah, no, it was fantastic. And again, thank you very, very much. Let's see, is there, okay. And then Hetty wants to ask you more about anthocyanin. as well offline. Okay, all right. It looks like we're good to go here. Oh, there we go. What sorts of issues did you run into making this the 1.1 Stellas? The
Yeah.
Stella 1.1s?
Yeah, in a nutshell, and Luke kind of alluded to this too. So, and this might come as a shock, but there is a difference in the capability for precision between NASA engineers and high school students. And so, like with the casing, Luke had kind of mentioned where it's just difficult to, So, for example, we bought wires that were larger because the 100 millimeter.
That's the
wires,
Q2, the
well, yeah,
yeah.
I'm getting to both, but
Okay,
so like for this one, like you have to put the wires in exactly the right spot to get it to close, right? So this was still feasible. For the 1.1, it was soldering, that you kind of had to know where the soldering was going to go and how much to do. And I don't know anything about soldering, to be honest. And our kids who were working on it were pretty good kids for that, but just a bit beyond their grasp. For them, I think they weren't expecting the challenges they got, and then they got busy with AP exams and those sorts of things, and it kind of fell by the wayside. So I think it could be done. You just have to know that there's minimal room for error on those, especially when it comes to the soldering. So I don't want to discourage anyone from doing it. I would just recommend start with the Q2, get comfortable with that, and then work your way up from there. If you're interested in like NDVI stuff. If you're planning on doing something like CO2 or air quality, the Stella is not going to help you with that. You would need something like the 1.1 or the 2.0. So again, I guess part of this is knowing what you want to do. But again, for us, the Q2 was a feasible entry point. And based on our experience, that's where I'd recommend starting.
Excellent. Yeah. And it is a good starting point. The soldering and the 1.1, yeah, was a bit more challenging for sure, especially the screen. And that's one of the things that we fixed in or I should say, Paul fixed in the 1.2. And it's very elegant. I just did a nice little video with Paul, and he's talking about like engineering and elegance and all that. Anyway, but it's fantastic. Thanks again. Is there any other? I don't see any other questions at the moment. So if that's everything, again, thank you very, very much for this, and we really appreciate you. And can't wait to talk to you again and see how things are going and what else we can help out with. So
appreciate it. Have a good night.
take care. Bye, everyone. Thanks for joining us.